Okay, so hello everyone again. This is lecture number 5 from the chapter System of Particles and Rotational Motion. In the previous discussion, we have started with the understanding of basically the analogy between your linear velocity, the translation motion concepts and the rotational motion concepts. Correct? So we have basically made an analogy between the velocity with angular velocity. And next, in just the last part, we just did a small discussion in which we understood that there is something which can be said analogous to your linear acceleration, which is basically called as angular acceleration. So let us try to understand this angular acceleration and then let's move forward. Okay. So this is lecture number 5 from the chapter System of Particles and Rotational Motion. I am Samir Lawankar. Let's begin our discussion. Okay. So currently we are on the sixth topic, that is your angular velocity and its relation with linear velocity. Okay, so we have completed introduction, center of mass, motion of center of mass, linear momentum of a system of particles, vector product of two vectors, and currently we are on the sixth subtopic, that is angular velocity and its relation with linear velocity. After this is being done, we will move on to the next concept, that is torque and angular momentum. Okay, fine. So let us move forward and let us understand now the new concept which I need to convey to you, that is basically angular velocity. Okay, sorry, angular acceleration. Okay, so what is basically angular acceleration? So it is basically defined a rotational motion which is analogous to a linear acceleration, and it is defined as, so let me just write, it is defined as rate or time rate of, it is defined as the time rate of change of velocity, time rate of change of velocity in translation motion. Okay, so it is defined as the time rate of change of velocity in translation motion. Okay, fine. So that thing being said, now next thing is so we define basically, and so we define, that is defined as the time rate of change of velocity, or basically it's angular velocity. Okay, so we define it basically as the time rate of change of angular velocity. Sorry, it's not translation, it's angular or rotational motion. Okay, so we define this alpha as basically in mathematical form, alpha is nothing but equal to d omega by dt. Okay, so it is basically d omega by dt. Okay, so therefore as here basically this omega is a vector, this omega is a vector, and this alpha is also a vector. Now just look at whatever I am writing. So if the axis of rotation is fixed, the direction of omega and hence that of alpha is fixed. Okay, so if the axis of rotation is fixed, direction of omega and hence that of alpha is fixed, because it's just d omega by dt, but direction would be same only. Okay, hence in this case, hence what we can write, the vector equation above can be reduced to, the vector equation reduces to scalar equation. So basically here we don't need to do a vector differentiation, we can simply do a what we can say scalar differentiation also. Hence the vector equation reduces to a scalar equation. So basically somewhere we can use, we will understand if the things persist, if problems come, we can understand whenever we will require a alpha vector equation definition and wherever we will require a scalar equation definition. Okay. So alpha is nothing but equal to d omega by dt. So here it's nothing but a simple scalar equation. Okay. So that's all I need to convey to you about omega and alpha. So that is the end of this subtopic. Now let us move on to the new concept, a very new concept. We will understand this concept for the first time. So just look at this very, very clearly. I will try to go very, very slowly here. We will understand these concepts. So let us start a new subtopic, which is basically your torque and angular moment. Okay. So in this section, we shall acquaint ourselves with two physical quantities, which are basically defined as vector product of two vectors. So I hope now you know what is basically vector product of two vectors. So we'll understand what are these, what will be those two vectors to be assigned here. So these, as we shall see, are especially important in the discussion of motion of systems or particles, particularly rigid bodies. Okay, so these are basically important for discussion of motion of system of particles, which are particularly rigid. Right. So that thing being said, let us understand the first concept, that is basically called as moment of a force. Moment of a force, or basically torque. Okay. So to understand the basic meaning of torque, let me first explain you using a simple example. So let us take this example. Okay. So let us assume this is a door. Okay. So this door is closed right now. And let us suppose it opens in this direction. Okay, so this is the direction in which it opens, correct? Or let us say we are standing in this form. We are standing here. Let us say our movement is in this form, and we are trying to push the door so that it moves in this direction. Okay, so basically, if you have seen very clearly, there may be some hinges located at this location. Okay, now, if you see clearly, if you try to use some suitable amount of force from this direction towards this force, towards this way, and similarly some force at this location towards this here. Okay, you will notice a difference in the amount of strain which goes to your hands or to your muscles. Okay, so the amount is different. We won't go into what is high, what is low here, but you may have seen that if you try to push it from this location and if you try to push it from this location, the amount is different. This is nothing but, if you see clearly, this is a rotational motion, and this is the concept which we are trying to study, that why is there a difference in the force. If the force applied is okay, force applied for translation motion, let us suppose this is a block and we are trying to push it. If you try to push it from here, if you try to push it from here, it won't make a much difference if it's only going under translation motion. But if it's going under rotational motion, you will see a difference in the values of this forces applied. Okay, so why is this a concept here? Let us try to understand that. No, so basically, first of all, let me make you understand this concept using this analogy only. Okay, so the rotational analog of force is moment of force. Okay, it is also referred to as torque or couple. It is also referred to as torque or couple, correct? So we shall use these words moment of force and torque interchangeably when the thing is required. So now let us define first of all the moment of force for a single particle. Okay, then we can use this, extend this concepts to your system of particles, including rigid bodies, right? So we shall now relate it to a change in the state of rotational motion, that is angular acceleration of a rigid body. So let us understand how these different concepts, such as angular acceleration, then vector product, etc., which you have studied in the previous lectures, will be applied. Okay, so let us go very slowly. Let us understand this concept very slowly, because this is very, very important as far as rotational motion is considered. Okay, so look at this diagram first of all. So here you can see that there is a particle P on which the force is acting in this direction. Let us say this is the direction of force here, right? And this, if this is your R value, so R can be extended and kept in this direction. This is the vector R. Okay, so let me just write also, because then it will be much more easy to make you understand. So if the force acts on a single particle at point O, whose position with respect to O is given by the position vector R, then the moment of force acting on the particle with respect to the origin O is defined as what? It will be defined as torque is defined as tau. Okay, so let me write only, so that will be okay. So if the force acts on a single particle, we are first understanding this about a single particle, and then we will extend it. Okay. So if the force acts on a single particle at a point P, if the force acts on a single particle at a point P, whose position with respect to the origin O is given by the position vector R, right? Then the moment of force. So this is torque is also called as moment of force. So the moment of force. So the moment of force acting on the particle with respect to the origin O, is defined as basically tau. So this is basically called as tau. Okay. So tau, that is torque, is basically equal to vector product of R with F. So this is nothing but your basic mathematical representation of moment of force, or basically torque. Okay. So here this is nothing but a Greek symbol which is called as tau. Fine. So what is let me change. Okay. So we got finally that torque tau is nothing but equal to R cross F. Fine. What is its magnitude? So the magnitude of this is nothing but equal to tau, which is equal to RF sin theta, where theta is the angle between F and R and F. Okay. So that thing is all explained to you. Now, next thing is, what is the dimensions of this force? Okay. Next thing is dimensions of torque. Okay. So what was the magnitude we finally obtained? We obtained the magnitude as nothing but equal to R into F into sin theta. Correct? What is R? R is basically meters. What is force? Force is nothing but equal to kg meter per second. Okay. So therefore, we can finally get this as nothing but equal to, in terms of LMT. So its length is 2. Correct? M is 1 and T is minus 2. Okay. Let me write it as MLT here, not LMT. So it's MLT. Right? What is M? M has a power of 1. What is L? L has a power of 2. What is T? T has a power of minus 2. Okay. Fine. So that thing is also explained here. Okay. Next thing is, so its dimension is same as that of work and energy. So it's just a observation. Okay, so dimension is same as that of work and energy, and but it is very different from that of what the work and energy explains to you, right? Because work is basically F into D. D is in meters only. That's why the dimension is coming same. But these two are very different concepts from each other. Okay. Okay. Next thing is, also we can also refer to this like this, that the magnitude of force, or basically this vector tau, is a vector quantity, but the work done is not a vector quantity, it's a scalar quantity. Okay. Next thing is about the SI units here. So what is the SI units? SI unit, simply you can cite force is Newton and R is in meters. So therefore SI unit is basically Newton meters. Okay. So this is basically Newton meters. Next thing we can also write it as, so if you remember correctly, for this complete axis and this rigid body shown, when we made a circle like this and obtained a value of O at this location, what we basically found that this was basically referred as R perpendicular, correct? Which was the perpendicular distance of this position P from this fixed axis of rotation, correct? Let us use that concept here. So basically now what we can write this tau as nothing but equal to R sin theta into F. Okay, what was basically R? R was this location, and let us say this is to be theta. So basically what is R cos theta? This is your R cos theta, and this is basically your R sin theta. What we can say here basically, this r sine theta, in the place of r sine theta, we can write directly r perpendicular cross f. Okay, that is the perpendicular distance of the line of action of f from the origin, and similarly we can also write it as f sine theta into r. Okay, so both are different things only, right? And now simple some interpretations. So when can tau be zero? So count tau can be zero in three different forms. The first thing is when f is zero. The second thing is when arc is zero, and second thing is when theta is equal to 0 degrees, or the angle between r and f is 0 degree. Okay, so there's the that thing is also explained. There's a moment of a force vanishes if either the magnitude of that force is 0 or if the line of action of the force passes through the origin. Okay, one may note that r cross f is a vector product. So properties of vector product of two vectors apply to it, and if the direction of f is reversed, let us say it is reversed, then the magnitude of r cross f will also reverse. Okay, so direction of moment of force is also reversed, and if the direction of both r and f is reversed, and the direction of moment of force is same only, because we understand the reflection property, that is minus r cross minus f is basically equal to r cross f. Okay, so basically the final conclusion is that as it is a vector product, it will follow all the concepts regarding your vector product properties. Okay, so final conclusion is only this much, that what is tau basically? Tau is basically equal to r cross f. This has to be remembered very correctly. It's not f cross r, it's r cross f. Okay, so people make generally a confusion. Generally, this thing is important here, because then the definition may change. The actual definition is that what is torque basically? Torque is basically r cross f. Okay, so I hope I made you understand this concept. So that thing being said, we are done with the first part of the subtopic, which is torque. Let us now understand the second subtopic, which is angular momentum. Okay, so again we'll start with the analogy concept only, and then we'll move forward. Okay, so if you remember correctly, what was linear momentum? So linear momentum is basically what? It is nothing but mass multiplied by velocity. Correct? Now let me just define first of all this angular momentum for a particle, and then we will move forward. Okay, so let us suppose, let me just write this line here. So consider a particle. So consider a particle of mass m, and linear momentum p, at a relative vector, at a relative position r, or let me write at a position r relative to at a position r bar related to the origin O. Relative to the origin O. Okay, so what will be the angular momentum? So the angular momentum which is L, right? Angular momentum L of the particle. So angular momentum L of the particle with respect to the origin, with respect to the origin, is defined to be, so please look at this relation also. So L is basically equal to R cross P. Okay, so what was torque? Torque was basically R cross F. What is L? L is basically R cross P. Okay, let us understand this relation more, discussion more. So first of all, let us calculate its magnitude. So what is its magnitude? The magnitude is simply L, which is equal to RP sine theta, where theta is the angle between R and P. Correct? In the place of R sine theta, we can also write it as R perpendicular into P. Okay, I hope this thing is also explained to you. Now, similarly, what we can also say, so when will L be 0? When can L be 0? L can be 0 in three different forms. If the R is 0, if your P is 0, and if your theta is equal to 0 degrees. That is the angle between R and P, 0 degrees. Okay, similar concept which you have involved in your, what we can say, this talk. Right, so that is the complete definition of angular momentum. Now let us try to do some more mathematical calculations here. So basically, when more research was being done, it was being found that the physical quantities we just understood right now, which were basically your torque and angular momentum, there was a relation between both of them. Okay, so let me just write that here. So the physical quantities, that is moment of a force, basically torque and angular momentum, have an important relation between them. So let us try to find out basically what is that relation. Okay, so first of all, we know that what is L? L is basically R cross P. Okay, let us differentiate this once with respect to time. So differentiating with respect to time, what we can get basically, we'll get dl by dt is basically equal to d by dt of r cross p. Okay, now look at this very carefully. So r cross p, this differentiation can be solved using a concept of differentiation which is called as chain rule. So what happens basically in chain rule, we divide it into this scenario. So it's dr by dt cross p plus r cross dp by dt. Okay, now look at this very carefully. Here we know that what is dr by dt? Dr by dt is nothing but velocity, right? And similarly, we also know that what is p? P is nothing but equal to m into v, right? So now look at this line very carefully. Therefore, you can write dl by dt is nothing but equal to velocity cross mass into velocity plus r cross dp by dt. So if you look at this relation very carefully, you will find that velocity is multiplied with some constant value into velocity only. So as these both will be in the same direction, the value of this is equal to 0. Clear? Okay. So therefore, what we are left up with, dl by dt is nothing but equal to r cross dp by dt. Now, if you remember correctly, this rate of change of linear momentum is nothing but equal to force. This is not equal to r cross f. And what is r cross f? It's nothing but tau. Okay. So therefore, we can basically say that dl by dt, which is nothing but equal to d by dt of r cross p, is nothing but equal to tau. Okay. So I hope I made you clearly understand the relation between both of them. So basically, if we will differentiate angular momentum, so the rate of change of angular momentum. So let me just write that. Just give me 1 minute. So the time rate of change of angular momentum of a particle is equal to the torque acting on it. So let me just write. So the rate of, or let me write it as time rate of. Okay, the time rate of change of the angular momentum of a particle is equal to the torque acting on it. Right, so this is nothing but rotational analog. So this is the rotational analog of which relation? Of the equation f is which is equal to dp by dt. Okay, f is nothing but equal to dp by dt, which basically expresses the second law of motion or translation motion of a single particle. Okay, so till now, what are the different concepts which we have understood, which were analogous in linear motion and rotational motion? Okay, so here basically we have related first of all velocity with angular velocity, then acceleration with your alpha, then force with your torque, then next is your linear momentum with angular momentum, and now just we got that this is here we write force is nothing but equal to dp by dt, and here we wrote torque is nothing but equal to dl by dt. So you can find that everything is being linked up similar to the case scenario of your linear motion. Okay, fine. So that is the end of your this concept also. Now let us move on to, so we have understood clearly the angular momentum for particle also and the moment of force or torque of the particle also. Now let us try to understand this concept for the system of particles. Okay, so we'll just add all these concepts here and try to understand this with this concept. Okay, so to get the total angular momentum, so first of all, let us try to calculate total angular momentum here. So total angular momentum for the system of n particles is basically equal to, so for the system of n particles, so for the system of n particles, we can write this capital L is equal to L1 plus L2 and so on till Ln. Correct? Which can also be done as equal to summation Li, I is from 1 to n. Clear? Okay, what is this Li value actually? This is nothing but equal to Ri cross Pi. Correct? And what is this Pi basically? This is nothing but equal to Mi cross, Mi multiplied by Vi. Okay, so this is simple multiplication only. I will just use nothing here. Okay, it is simple multiplication mi into Vi. That is a linear momentum. Correct. So that thing is also explained. Now let us find the generalization of this definition for angular momentum of a single particle to go with your system of particles. Okay. So here let us try to differentiate this equation. So differentiating equation 1. So differentiating equation 1 with respect to time. So what we will get? We'll get dl by dt is nothing but equal to dl1 by dt plus dl2 by dt plus and so on till dln by dt. Right? I hope it is clear. What are these terms? These terms are nothing but tau I. So I mean not tau I, it's tau 1. It is nothing but tau 1 plus tau 2 and so on till tau 1. Okay, so that thing is also explained to you. Now what is basically tau I? Tau I is nothing but equal to R cross Fi. Right? And what is this basically Fi? Fi is basically the force acting on this particle, which is basically your internal plus external. Internal plus external. Okay, so now we are trying to relate just the concept we understood for linear momentum to the concepts of your external, what we can say, torque also. Okay, so I will go slowly. So now what we can write, basically you can write tau, complete tau is nothing but equal to summation of tau I, right? Which is nothing but equal to summation of Ri cross Fi, right? But here what is tau I basically? Tau I is basically equal to tau internal plus tau external. Correct? Where what is tau internal? Tau internal is basically summation Ri cross F internal. And what is tau external? Tau external is basically summation Ri cross F external. Simple mathematical input, nothing complex here till now. Now let us understand more. Okay. So now again using the Newton's third law, what we can say that the forces between any two particles of the system are equal and opposite. So, and also those forces are directed along a joining of those two particles. So in this case also the contribution of internal forces to the total torque system would be zero. Okay. So therefore what we can write here again, I will just write the last line and give the reasoning in the brackets. So basically here also the contribution of the internal forces. So the contribution of internal forces to the total torque on the system is zero. The system is zero since the torque resulting from each action reaction plane of force is zero. So the reason of this can be said directly as Newton's third law of motion. It is equal to Newton's third law of motion. Okay, so we can basically write that. So therefore tau internal is equal to 0, and tau is basically equal to tau external only. Okay, so therefore finally what we can write basically that dl by dt, right? This dl by dt is nothing but equal to tau external. Please remember, if you have seen something like this before also, we have seen the same thing for your linear momentum also. That is when dl by dt is nothing but equal to, dp by dt is nothing but equal to f external. Okay, so that just leaves us to understand the next concept here. First of all, let me just explain this again. So what does this dl by dt upon tau external gives you? So let me just write this also. So here the time rate of, I will just write. So the time rate of the total angular momentum, of a system of particles, about a point is equal to the sum of the external torques. Is equal to the sum of external torques. Okay. Let me write more. Acting on the system taken about the same point. Acting on the system taken about the same point. Right. So this is the final conclusion here. It is nothing. So this is how we basically generalize the complete statement for a system of particles. Okay. So just a simple note that when we have only one particle, there are no internal forces or torques. Then also this same thing can be happen. Okay. We can just write the same thing for our single particle also. Okay. Let me write one more thing. So it is the rotational analog of. It is the rotational analog of the equation, that is dp by dt is nothing but equal to f external. Okay, fine. So it holds, so that thing is explained. So now as we related dp by dt with something equal to f external, so we basically said that when f external of a system of particles is equal to 0, then dp by dt is 0, and if dp by dt is 0, we say that p is conserved, right? So let us go with the same concept here and understand that concept here also. That is basically the conservation of angular momentum. Okay, so what will happen here? Same analogy will be put forward here. So let me just write this and then let us close the discussion. Okay, so if tau external is equal to 0, then the equation reduces to, then the equation becomes dl by dt is equal to 0. So what does this line mean? This basically line although means that L is constant. L is a constant. Okay, so just let me write also so that this mathematical thing can be written in some sort of statement. So if the total external torque, it is very important, it's external torque here, right? Where the total external torque on a system of particles, okay, is zero, then the total angular momentum, of the system is conserved, right? That is remains constant. So as the same analogy which we referred in previous concept regarding the conservation, so let us say that this L is written in terms of some Lx I cap plus Ly j cap plus Lz k cap, because it's a cross vector product of R cross P, therefore this will be also a vector. So we can simply write this Lx is nothing but equal to some k1, this Ly is nothing but equal to some k2, and this Lz is nothing but equal to some k3, where this k1, k2, k3 are constants. Right? So that thing is also explained to you, and therefore the statement basically means that the total angular momentum is conserved. Uh, and also the each of these components of the momentum, angular momentum is also constant. Obviously, they are also conserved. Okay, fine. So we have finally completed the conservation law for linear momentum of a system of particles also, and the conservation of angular momentum of a system of particles also. Right? In the subsequent slides, the subsequent chapters, we will see how this information of conservation of angular momentum can be utilized in different concepts. So we will understand that all topics in subsequent lectures. Let me pause it here only. In the next lecture, we will first of all do a simple question, understanding the torque and the angular momentum, and then we'll move forward. We'll start with a question on torque, and then we'll move forward. Okay, so let me stop this discussion here only. Okay, so the simple course progress for you. So we started with introduction, went on to understand the center of mass, then went on to understand the motion of center of mass, in which we also understood that mass times acceleration of center of gravity, total mass multiplied the product of total mass and the center of acceleration of the center of mass is nothing but equal to force external. Then in linear momentum of a system of particles, we understood that if force external is equal to 0, we say the total linear momentum of the system of particles is conserved. And we understood vector products, properties of vector products in fifth subtopic. Then we understood about angular velocity, angular acceleration in this concept in sixth subtopic. And then in seventh topic, which is going on, we understood torque, that is nothing but equal to R cross F. This is nothing but equal to R cross F. And angular momentum is nothing but equal to R cross P. Also, in the final discussion just before this, we've understood that the rotational analog of F is equal to dp by dt is nothing but equal to tau external, or F external is equal to dp by dt is nothing but equal to your tau external is equal to dl by dt, d capital L by dt. And hence we can say that if torque external on the body is 0, on the system of particles is 0, then we can say that the angular momentum of the system is conserved, or angular momentum of the system is constant. Right? So let me stop it here only. In the next lecture, we'll move forward. So thank you for now. We'll meet in the next lecture. So thank you so much.